In the previous lecture, we have discussed that what is meant by statistical testing and what is the concept of statistical null hypothesis and statistical alternate hypothesis, and how these are used in sorting out the biological problems and how they are linked to the statistical analysis or statistical testing. And then we also saw the definition of one-tailed and two-tailed test. So from now onwards, we are going to start the statistical tests that make use of the statistical null hypothesis and alternate hypothesis, and we will see that how these tests they are executed, that how we formulate our null hypothesis, how we formulate our alternate hypothesis, and how do we do these calculations. So we will do the simple statistical tests, the basic statistical tests, and we will start from those tests which involve the analysis of frequencies. For example, if you have your data or if you have your observations in a form which are the frequencies of your variable, which are the counts or frequencies of your variable in different categories or in different classes. So how you can analyze your data. So the simple test that we can use for the analysis of frequencies is the chi-square test. So in chi-square test, the observed frequencies are compared with expected frequencies on the basis of some null hypothesis. So in this case, you have your observed frequencies that you have taken after your sampling or after your experiments. So these observed frequencies, they are compared with the expected frequencies on the basis of some null hypothesis. It means that you are going to compare your observed frequencies with some expected frequencies on the basis of some model which you built according to your null hypothesis of the experiment. So this is a simple calculation, and this is not the letter X, this is the Greek letter chi. O means observed frequencies and E refers to the expected frequencies. So this is the simple formula of the chi-square test, and there are different forms of the chi-square test that make use of the same formula, but their null hypotheses are different. And the three basic types of the chi-square test, they include the chi-square test of homogeneity, goodness of fit chi-square test, and the chi-square test of independence. So general procedure in any kind of the chi-square test is that first of all, whenever you have your samples or whenever you have your observations, you have to choose the type of chi-square test on the basis of your experiment, that what kind of experiment are you doing, what is your experimental hypothesis, right? So you have to choose the type of chi-square test that you're going to use. And then you have to state the statistical null hypothesis and alternate hypothesis for your statistical test. And then you have to calculate the expected frequencies on the basis of null hypothesis, because you already have your observed frequencies on the basis of the experiment, on the basis of sampling that you did. So now you have to calculate the expected frequencies under the null hypothesis that you have proposed. And then do the calculations, do these calculations and calculate the value of chi-square, which is your test statistic. So what is the next step when you do the test statistic? So when you have your test statistic, what do you do with that? We discussed in the previous lecture. So when you have your test statistic, when you have your calculated value, you compare it with the tabled value of that specific test. So now you have to compare test statistic, which is the calculated value of chi-square, with the tabled value from the chi distribution table. And after you have done this comparison, you're going to state your results, that whether your results are significant or your results are not significant. So this is the general procedure for any kind of the chi-square test that you're going to use. Now, starting from the chi-square test of homogeneity, this is the simplest type of the chi-square test, and it is the test for homogeneous frequencies. So in this test, the assumption is that the frequency distribution is uniform in all classes or categories. So all of the classes or categories that you have, the frequency distribution of your variable is uniform in all of those classes. It should be homogeneous, that there should be no difference, there should be no significant difference in frequency distribution of your variable among different categories or among different classes. So this is the basic assumption of the chi-square test of homogeneity, which is the test for homogeneous frequencies. And we are going to take the example of Dixella insects. So a biologist collects a sample of Dixella pupae from a pond, and these pupae, they are morphologically indistinct. They are morphologically similar to each other, and they emerge out in following numbers: Dixella autumnalis, Dixella aestivalis, Dixella amphibia, and Dixella attica. So these are the 4 species of the Dixella that are present in that community, that are present in that pond, and they emerge out in these numbers: Dixella autumnalis 24, Dixella aestivalis 32 out of the 75 pupae, Dixella amphibia 10 out of 75 pupae, and Dixella attica 9 out of 75 pupae. So this is their frequency distribution. So these species, they are the classes, they are the nominal categories, and these are their frequencies, which are the number of pupae belonging to respective species. So this is the kind of distribution that you get. So unless and until you have some previous observation or previous finding that what is the species composition in that community or what is their relative distribution, so unless and until you have that, you have to assume that these are homogeneously distributed, that their distribution should be homogeneous. So apparently we can see that these are not homogeneous. So out of 75, Dixella attica is only 9 and Dixella aestivalis is 32. So apparently we see that there is a difference between their frequencies. So now we want to confirm that whether this difference is a significant difference or this difference is not a significant difference. So for that purpose, we are going to use the chi-square test of homogeneity. So question is the distribution of frequencies between the categories homogeneous? So this is our question. And we are going to use the chi-square test of homogeneity. So what is the next step? The next step, after stating the problem and after choosing the type of the chi-square test that we are going to use, we have to state the alternate and null and alternate hypotheses. So our null hypothesis is the observed frequencies are homogeneous and the departure is merely due to the sampling error or scatter. So this is our null hypothesis, in which we are assuming that this difference is non-significant and this difference is only because of some sampling error or scatter. And then the alternate hypothesis is the observed frequencies depart from those expected of a homogeneous distribution by an amount that cannot be explained by sampling error alone. So in the alternate hypothesis, we're assuming that this difference is significant, and this difference is significant enough not to be accounted only by the sampling error. So these are our null hypothesis and the alternate hypothesis. So what is the next step after we have stated our null and alternate hypothesis? The next step is calculation of expected frequency on the basis of the null hypothesis that we have stated. So our null hypothesis was that the frequency distribution in all of these classes is homogeneous. So if our null hypothesis is true, we expect that 75 pupae should be distributed homogeneously between the 4 nominal categories. And for that purpose, we will do the calculation, which is how many categories or classes do we have? We have 4 classes. So 1 by 4 into 75, which is the total number of observations. So 75 divided by 4 is 18.75. So 18.75 number of pupae should be present in every category. And this is the table for the calculation of chi-square value, and the chi-square value can be calculated by using this kind of a simple table. And in this table you can see that there are different columns. So the first column refers to the column in which we have stated our classes or our categories, and in this case these categories are the names of the species of these insects. So in the second column we have the observed frequencies that we have observed, and in the third column we have the expected frequencies, And as you can see that the total of the observed and expected frequencies, that should be same. And then in the next column we have the difference of observed and expected frequencies, which is O minus E. And then in the next column we have the square of this difference between observed and expected frequencies. And in the last column we have this square of the difference divided by the expected frequencies. So as you can see that we have to do this calculation separately for every class, and then we take the sum of the last column, and that sum is actually our chi-square value. So this is the method of calculating the chi-square value from your observed and expected frequencies. Now the calculations, the observed frequencies and the expected frequencies. Then we have the difference of observed and expected frequencies. So 24 minus 18.75, which is 5.25, 32 minus 18.75, which is 13.25, and then 10 minus 18.75 minus 8.75, 9 minus 18.75, which is minus 9.75. So you have to ignore this minus sign in the last two rows. Why? Because we are going to take square of these values in the next column, so it's not going to make any difference if there is a minus sign or if there is a plus sign with your values. So we are going to take the square of these individual values. So square of 5.25, which was the difference of observed and expected frequency of Dixella autumnalis. Then the square of 13.25, which was the difference between observed and expected frequency of Dixella aestivalis. And then the square of 8.75, which was the square of difference between the expected and observed frequencies of Dixella amphibia. And then the square of 9.75, which is the difference between observed and expected frequency of Dixella attica. And then we have our last column, in which we divide this square of the difference between observed and expected frequencies by the expected frequency. So we have this 27.5625, and why I'm taking this long number is because when we round off during the initial stages of calculations or during these intermediate steps of calculations, we are going to end up with a different number and we are going to have a different result. So we have to take at least 4 digits after a decimal so that we have the precise calculation at the end. So 27.5625 divided by the expected frequency, and the result is 1.47. So we calculate that for every class. For Dixella aestivalis, the square of the difference divided by the expected frequencies is 9.3633. For Dixella amphibia, it is 4.0833, and for Dixella attica, it is 5.07. And now we have to take the sum of these values, 1.47 plus 9.3633 plus 4.0833 plus 5.07, and our sum is 19.987. So this is the value of our chi-square. This is our calculated value. Now our calculated value is 19.987. So what should be the next step? Next step is to see what is the degree of freedom, which is n minus 1. N is the number of classes, minus 1 is 3. So our next step is to see that what is the probability of a null hypothesis to be true. And for that purpose, we have to compare our calculated value with the tabled value. And our null hypothesis is the observed frequencies are homogeneous and the departure is merely due to sampling error or scatter. So we are going to compare our calculated value with our table value to see that whether this null hypothesis is true. What is the probability of this null hypothesis to be true or no? So this is our chi-square distribution table. And in this table, as you can see, that we have the columns which represent the probability values for different levels of significance, and they are arranged in the rows according to the degree of freedom. So what was our degree of freedom in this case? It was 3. So what is our first level of significance? It is 0.05. and the value is 7.815. So what was our calculated value? Our calculated value was 19.987. So which one is greater, our calculated value or the table value? Obviously our calculated value is greater, 19.987. It means that we reject null hypothesis in favor of alternate hypothesis. And the significance level is 95%, which is said to be significant. Now we are also interested in seeing that what is our next significance level, that at this step we reject the null hypothesis. So null hypothesis stands rejected at this point. So in the further steps we are only going to see that what is our maximum significance level of these results. So what is our next level of critical probability or significance? It is 0.01, and what is the value there? It is 11.345. So this value is also less than the calculated value, therefore this result is also significant at 99% significance level. So this result is highly significant. And now we move on to our next level of critical probability of significance, which is 0.001. And here we can see that our calculated value is also greater than this value. This is 16.266, the table value at 0.001, significance level of 99.99%. So our results are very highly significant, that there is a 99.99% probability that our null hypothesis is false, right? So probability of a null hypothesis to be true is less than 0.001. Therefore, we are rejecting a null hypothesis and we are accepting the alternate hypothesis. So what should be our results? This is our last step, the results. There is a statistically very highly significant departure from homogeneity between the four categories. Chi-square 19.987 and probability less than 0.001. Distribution of the four species is not homogeneous in the population. So this is another way to state our results, that we say that the distribution of the four species of Dixella is not homogeneous in the population, in the community, and stating the chi-square value and the probability of significance of these results. So this is how we do the chi-square test of homogeneity, and this is how we state our results. Our next type of the chi-square test is the chi-square goodness of fit test. So as its name indicates, that it is comparison of observed frequencies to an expected predetermined model or ratio. It means that we are not assuming them to be homogeneous, or we are not assuming them to be the same in all categories. Rather, we are assuming that these frequencies, they should appear in a pattern, they should appear in a ratio. And we are going to check, we are going to test that whether our observed frequencies, they fit into that ratio or no. So what is the goodness of fit of our observed frequencies into those expected under that predefined ratio? And we are going to use the Mendelian ratios, for example, the law of independent assortment. So you remember that what is the phenotype ratio, what is the expected phenotype ratio? It is 9:3:1. So this is the phenotype ratio for the law of independent assortment. So a farmer did a dihybrid cross of pea plants, and the plants were heterozygous for two traits. So these two plants, they were heterozygous for two traits, and he did the dihybrid cross of these pea plants. And these two traits were seed appearance and color. So this is the very famous example that every biologist, every biology student, that they study during their courses. So this is a very basic example of genetics, and you all must be familiar with these examples. So that is why I have taken this example. This is the example of law of independent assortment. So this farmer obtained a progeny of 556 seeds. Out of these 556 seeds, 315 were round yellow, 108 were round green, 101 were wrinkled yellow, and 32 were wrinkled green. So these were his results. Now the question is, does the result of this cross follow the Mendel's law of independent assortment? So this is the biological question, or this is the statistical problem that we have, that does the result of this cross follow the Mendel's law of independent assortment. The next step is to state the alternate hypothesis. Our alternate null hypothesis. Our null hypothesis is the observed frequency distribution follows the Mendel's law of independent assortment. And our alternate hypothesis is the observed frequency deviates from the Mendel's law of independent assortment. So these are our hypotheses. The next step is calculation of expected frequency, and how we do calculate the expected frequency on the basis of our null hypothesis. So our null hypothesis is that this cross, the results of this cross follow the Mendel's law of independent assortment. So therefore the phenotypic ratios should be 9, 3, 3, 1. So we calculate the expected frequencies on the basis of this model. So first of all, we calculate their ratios, we calculate their proportion values. So round yellow, 9 by 16. So what is the total of 9, 3, 3, 1? It is 16. So 9 by 16 is 0.5625. 3 by 16 is 0.1875. And 1 by 16 is 0.0625. And now we calculate the expected frequency. What is the total number of the progeny that the farmer had? These are 556. So 0.5625 out of the 556 should be the observed frequency for round yellow, which is 312.75. And for round green and wrinkled yellow, it is 104.25 each. And then for the wrinkled green, we have 34.75, and their total is 556. So this is how we calculate the expected frequency. So we are not considering them to be homogeneous, we are considering them to be following a predetermined ratio. And now the table for the calculation of the chi-square value. We have observed frequencies, we have expected frequencies, the total is same. So next step is the calculation of difference between observed and expected frequencies. The difference between the observed and expected frequency of round yellow seeds is 2.25. The difference between the observed and expected frequency of round green is 3.75. The difference between the observed and expected frequency of wrinkled yellow is 3.25, and the difference between the observed and expected frequency of wrinkled green is 2.75. And what is the next step? To take the square of these values. The difference between the observed and expected frequency of round yellow, the square of 2.25, and the square of 3.75, the difference between the observed and expected frequency of round green. Then 3.25 square, the difference square of the difference between the observed and expected frequencies of wrinkled yellow. And then 2.75, which is the square of difference between the observed and expected frequencies of wrinkled green. Now we are going to divide this difference with the expected frequencies. So 5.0625, which is the square of the difference between observed and expected frequency of round yellow, is divided by the expected frequency of round yellow. And we have the value, which is 0.0162. So we do the same calculation for round green, for wrinkled yellow, and for wrinkled green. Now we take the sum of these individual values, 0.0162 plus 0.1349 plus 0.1013 plus 0.2176, and their sum is 0.47. So this is the value of the chi-square that we have. So what should be our next step? Next step is to define the degree of freedom and to compare this calculated value with the tabled value of chi-square. So our degree of freedom is, because there are 4 classes, so degree of freedom is 3. The table value that we took from the table of chi-square distribution is 7.815 at probability of 0.05. And as we can see that our calculated value is less than the table value at probability 0.05, so we are going to accept the null hypothesis. So the probability of null hypothesis to be true is greater than 0.05, therefore the results are non-significant. And therefore we are free to state that the result of cross follows the Mendel's law of independent assortment. The chi-square value is 0.47 and the probability of this value is greater than 0.05. So this is how we do the chi-square goodness of fit test. Then we have another example of the chi-square goodness of fit test, and this example is about the species composition of ground foraging birds, and 64% of the ground foraging birds in that area, they are sparrows, 29% are larks, and 7% are francolins. And these observations, they were made on the studies that were done in the past from that area, that 64% of the ground foraging birds are sparrows, 29% are larks, and 7% are francolins. So this is the frequency distribution that we have in that area. And then after 30 years, a new study was done to find out that if the species composition is same as previously found, or has it changed over the period of time. So 750 birds were observed, and out of those 750 birds, 495 were sparrows, 198 were larks, and 57 were francolins. So this was the species distribution in the new observation. Now the question is there any change in species composition, or is the species composition same as previously found, or it has changed? So this is the question that we are going to check. So again, we are dealing with the frequencies, so we have to apply the chi-square test. And what kind of chi-square test? The chi-square goodness of fit test, because we have a pre-existing ratio, the pre-existing relative frequencies of different nominal categories. So the next step is to state the null and alternate hypothesis. Our null hypothesis is there is no change in species composition of the area, and it is same as previously studied. And alternate hypothesis, obviously it assumes a difference, and it says that species composition is different from previous study. So these are our hypotheses. Next step is calculation of expected frequency under our null hypothesis, and this is how we do it. So sparrows, according to the previous study, they were 64% of all ground foraging birds, larks were 29%, and francolins were 7%. So this is how we calculate their proportions, that 64% means 64 out of 100, which is 0.64, and then 29 out of 100, which is 0.29, and 7 out of 100, which is 0.07. And the expected frequency in the 750 birds that were observed, the expected frequency is 0.64 into 750, which is 480 for sparrows, and 217.5 for larks, and 52.5 for francolins. So these are our expected frequencies. Now we have to apply the test. This is our chi-square calculation table, the observed frequencies and the expected frequencies, and you can see that their sum is similar. Then the difference between the observed and expected frequencies, it is 15 for sparrows, 19.5 for the larks, and 4.5 for francolins. Again, you have to ignore the minus value because we are going to take the square of this difference in the next column. So 15 square, which is the square of difference between observed and expected frequencies of sparrows, 19.5 square, which is the square of difference between the observed and expected frequency of larks, and 8.75 square, which is the square of difference between the observed and expected frequency of francolins. And what is our next column? Our next column is that this square of the difference between observed and expected frequency is to be divided by expected frequency of that class. So 225 is the square of difference between the observed and expected frequencies of sparrows, and it is divided by the expected frequency of sparrow, and we get 0.4688 value. And then we divide the square of difference between observed and expected frequencies of larks with the expected frequency of larks, and we get 1.7483. And then we divide the square of difference between the observed and expected frequencies of francolins, and we divide that by the expected frequency of francolins, and we get the value, which is 0.3857. Now we take the sum of these values, 0.4688, 1.7483, and 0.3857, and their sum is the value of our chi-square, which is 2.60. So this is our chi-square calculation. The next step is that we have to check that whether this chi-square value is significant or no. So degree of freedom in this case is 2 because there were 3 classes, so 3 minus 1 is 2. The table value that we checked from the chi-square distribution table is 5.991 at probability of 0.05 and degree of freedom 2. So which one is greater, our table value or our calculated value? Our calculated value is less than the tabled value. Therefore, we have to accept the null hypothesis. So probability of null hypothesis to be true is greater than 0.05, which means our results are non-significant. So there is no change in species composition, chi-square 2.62, and probability greater than 0.05. Or we can also say that species composition is same as previously found. The chi-square is 2.6 and the probability is greater than 0.05. So this is the example that how we can use the chi-square goodness of fit test to compare our observed and expected frequencies under some predetermined model or predetermined ratio. So this is the exercise that you have to do at home and share with me the results and discuss with me the results. And if you have any problems in solving this exercise, we will discuss that in the question answer session. So example is the total number of weeds and quadrats collected from different fields. So these are 6 fields, and these are the number of weeds that are found in these fields. So the question is there a significant difference in the weed infestation among different fields? So we have the same observation, we have the same example with different observations, and the question is also same, is there a significant difference in the weed infestation among different fields? So you have to solve this problem and share the results with me, and you have to follow all the steps, and then you have to come up with a proper result statement in the same format that I have provided you. And this is another exercise. In a dihybrid cross, a progeny of 3,839 seeds was obtained with following categories. So this is another example, and the question is, does the result of this cross follow the Mendel's law of independent assortment? So again, you have to state your hypothesis, you have to choose that what kind of statistical test you are going to use, and then you have to calculate your expected frequencies under your proposed null hypothesis, and then you have to calculate the chi-square value, compare it with the table value, and after you have done your comparison, then you have to state your results in a proper form. So this is all for this lecture, and in the next lecture we will discuss the other type of the chi-square test, which is the chi-square test of independence. Okay, in the previous lecture we had studied the introduction to chi-square test. Chi-square test is used for the analysis of frequency. So whenever you have the count of numbers in different nominal categories, or you have frequencies of observations in different nominal categories, then you apply the chi-square test for the comparison of those frequencies. And we saw three main types of the chi-square, three basic types of the chi-square test, which are chi-square test of homogeneity, the chi-square goodness of fit test, and the chi-square test of independence. So in the previous lecture we had discussed the two types of the chi-square test of homogeneity and the chi-square goodness of fit test. So chi-square test of homogeneity is used when all the nominal categories, they are supposed or they are assumed to have equal frequencies. So frequency distribution should be homogeneous in all of the nominal categories. So to test that homogeneity, we use a chi-square test of homogeneity. Then the chi-square goodness of fit test. So if we don't assume them to be the frequencies to be homogeneous, rather we assume that these frequency distribution patterns, they should follow a trend, or they should follow a predetermined ratio. Then we have to apply the chi-square goodness of fit test, that how much or how good our observed frequencies they fit into the model, how good they fit into the predetermined ratios. So for that purpose we use the chi-square goodness of fit test. So now we are coming to the third type of the chi-square test, which is the chi-square test of independence, and this test is also known as the test of association. And this test is used to test the independence of two categorical or nominal variables. So in the previous two examples we had seen the test which employed only one type of the variables. The number of categories were many, like the number of categories could be 2, 3, 4, 5 and so on, but the type of variable in the chi-square goodness of fit and the chi-square test of homogeneity, so the number of the variables was only one, the variable was only one. But in this case, in this chi-square test of independence, we can test the independence of two categorical or nominal variables with each other. So in this case we can use two or more than two variables. So if you are interested to find out if the two categorical variables or the nominal variables, they are associated or related, which means they are dependent on each other or they are independent of each other, so we can test that through the chi-square test of independence. And until we have an evidence to assume that they are associated, we must assume that they are not. So this is the basis of the null hypothesis, that we have to assume that they are not associated with each other, they are independent of each other. So in the population, two categorical variables are independent or they are not associated. This is our null hypothesis. And the alternate hypothesis is, in the population, two categorical variables are dependent. Or in other words, we can say that in the population, two categorical variables are not associated. And the alternate hypothesis is, in the population, two categorical variables are associated. Now we will see an example that a biologist collects leaf litter from quadrate, and these quadrates are placed randomly at night on the ground in two woodlands, one on clay soil and other on chalk soil. And then he sorts through the litter and picks out wood lice of two species, Oniscus and Armadillidium. Now the question is there any association between soil type and wood lice species? So null hypothesis is there is no association between soil type and wood lice species. And the alternate hypothesis is there is an association between soil type and wood lice species. And observations are presented in a contingency table. So these are the observations. So why we are applying the chi-square test of independence? Because our question is to test the association between two variables. And what are these two variables? One variable is the type of soil, which is either the clay soil or the chalk soil. And the other variable is the type of species of wood lice, which is either Oniscus or Armadillidium. So these are the two variables, so that is why we are using the chi-square test of independence. And we have stated our null hypothesis and alternate hypothesis, and these are the observations that biologist made. So these observations are presented in a contingency table. So what is meant by a contingency table? So a contingency table is a table that shows the distribution of one variable in rows and of another in columns. And it is used to represent two-way classification. So what is meant by a two-way classification? A two-way classification is when two categorical observations are obtained from a sampling unit. So it means that each observation in a contingency table, that observation represents two variables at a time, right? So this is meant by a two-way classification. So a contingency table has several rows and columns in it, and this is referred to as R by C contingency table, where R represents the number of rows and C represents the number of columns. And the simplest type of the contingency table is a 2 by 2 contingency table. So 2 by 2 contingency table has 2 rows and 2 columns. So it means that each of the 2 variables has 2 nominal categories. But it can have more than 2 nominal categories. So this is a contingency table. So now we are going to take the examples of the contingency tables to understand the properties of the contingency table. So remember these two aspects of the contingency table, the two-way classification, which is presented by the blue color, and the other aspect is 2 or more than 2 nominal categories, which is presented by the green number. So here we have the contingency table that we were talking about. So this is a 2 by 2 contingency table, and in this table you can see that there are two variables. One variable is presented in rows and the other variable is presented in columns. So the variable which is presented in rows is the type of soil, and it has two nominal categories, the clay soil and chalk soil. And the variable which is presented in columns is the type of species, and it also has two categories, Oniscus and Armadillidium. So that is why it is a 2 by 2 contingency table, because each of the variable has two nominal categories. So number 25 here, the cell which contains the observation 25. So this 25 is the number of Oniscus in clay soil. So this number 25 is a two-way classification because it represents two variables at a time. And then the number 20, so this is Oniscus in chalk soil. And then number 8, it represents Armadillidium in clay soil, and number 23 represents Armadillidium in chalk soil. So this is what is meant by a two-way classification, that each of these observations, each of these cells in a contingency table, they represent two variables. And why it is a 2 by 2 contingency table? It is 2 by 2 contingency table because each of the variables has two nominal categories. Now, one-way classification for the same example. So what is a one-way classification? In which only one variable is given. So this is the same example, and we are presenting a one-way classification of this example, that the type of species, Oniscus and Armadillidium. So you can see that there is only one variable, and this is why it is a one-way classification. So a contingency table has a two-way classification in which there are two variables. But a simple one-way classification is that in which there is only one variable. Now let's take another example to understand the concept of the two-way classification and a contingency table. So this is a one-way classification in which the weight of students is measured, and there are 6 classes of the range of the weight of students. And then there are frequencies, that the number of students having a weight between 41 and 50 kilograms, and then 26 is the number of students having weight between 51 and 60 kilograms, and so on. So what if we add another variable? Because this table has got only one variable, and that variable is the weight of students. So what if we add another variable to this classification? So it will become a two-way classification. And if we add another variable, which is the gender of students. So now we have two variables, which is the gender of students, which is presented in columns, and it has two categories, females and males. And then the other variable is the weight of students in kilograms, which is presented in rows, and it has 6 classes or 6 categories. And the observations, they belong to two variables, the gender of students and the weight of students. So number 10 here are the females with a weight in the range of 41 to 50 kilograms. 14 are the females with a weight range of 51 to 60 kilograms, and so on. So this is a two-way classification, and this is meant by this is what is meant by the contingency table. And a contingency table is not simply a 2 by 2 table, but it can have more than 2 categories. Taking other examples of the contingency table, so here we have a 2 by 4 contingency table. So in this 2 by 4 contingency table, you can see that there are 2 rows and there are 4 columns. So what are the 2 rows? These 2 rows, they represent the diet recommended by the American Heart Association, and the diet which is Mediterranean. And then in the columns, we have the health status of individuals, the cancer cases, non-fatal heart disease cases, fatal heart disease cases, and healthy individuals. So this is a 2 by 4. So diet is presented in rows, and the other variable, which is the health status, it is presented in columns. So 15, this observation or this cell, it represents the number of cancer cases on American Heart Association recommended diet. And 7 represents the number of cancer cases using the Mediterranean diet. 24 is the number of the non-fatal heart disease cases on AHA diet, and 14 is the number of non-fatal heart disease cases on Mediterranean diet. Then 25 is the number of fatal heart disease cases on AHA diet, and number 8 is the number of fatal heart disease on Mediterranean diet. Then 239 are the number of healthy individuals on AHA diet, and 273 is the number of healthy individuals on Mediterranean diet. So this contingency table has two variables, the diet and the health status. And one variable is presented in rows and the other variable is presented in columns. So this is a 2 by 4 contingency table. Why it is a 2 by 4 contingency table? Because the rows, they have 2 categories and the columns, they have 4 categories. So that is why this is a 2 by 4 contingency table. And now we have another example, which is a 3 by 3 contingency table. And in this table, you can see that again, the 2 variables, they have 3 nominal categories each. One variable is presented in rows, and that variable is the pH of water. And one variable is presented in columns, which is the species of protists which are found in that water. So this is 3 by 3. So there are 2 variables, the species and the pH. And the pH has 3 categories and the species also has 3 categories. So this is a 3 by 3 contingency table. So 16 here represents the number of Eurotricha castalia in the pH of 5 to 7. 24 is the number of Eurotricha castalia in the pH of 7 to 9, and 11 is the number of Eurotricha castalia in the pH of 9 to 11. And then 37 is the number of Chlamydomonas acidophila in the pH of 5 to 7. 22 is the number of Chlamydomonas acidophila in the pH of 7 to 9. And 8 is the number of Chlamydomonas acidophila in the pH of 9 to 11. And then we have our last column, which is the Cryptomonas curvata. So 16 is the number, which is the number of Cryptomonas curvata in the pH of range 5 to 7. 25 is the number of Cryptomonas curvata in the pH range of 7 to 9. And 12 is the number of Cryptomonas curvata which are found in the water with a pH in the range of 9 to 11. So these are the contingency tables. So a contingency table has a two-way classification system in which each observation represents 2 variables at a time. And a contingency table can have, it can be simple, it can be 2 by 2, or it can have more than 2 nominal categories. It could be 2 by 4, it could be 3 by 3, it could be 4 by 4, it could be 4 by 6, 4 by 5, or 5.5 by 4. So this is the concept of contingency table. Okay, and now coming back to our example that we were discussing. So our example was that the quadrants were placed into 2 woodlands, and then the number of the woodlice species were counted. So the question is there any association between soil type and the woodlice species? And the null hypothesis that we stated is there is no association between soil type and woodlice species. And the alternate hypothesis is there is an association between soil type and woodlice species. And this is the observation, and these observations are presented in a contingency table. Now, after stating the null hypothesis and the alternate hypothesis, what is the next step in chi-square? The next step is to calculate the expected frequencies. So the expected frequency of a cell in a contingency table, it is calculated by the formula which involves the multiplication of row total with column total, and then this is divided by the grand total. So TR, which is the row total, and TC, which is the column total, they are multiplied, and then their answer is divided by the grand total. So here we have our example, the example of the woodlice species in two types of soils, and these are the observed frequencies. So you can see the row totals and the column totals. So 33 is the row total of row number 1, which represents clay soil and the two woodlice species. And then 43, it represents the total of the rows, which represents chalk soil. And then 45 is the total of the column number 1, which belongs to the Oniscus species in the two types of soils. And then the 31 number, this is the sum of the column number 2, which is Armadillidium in the two types of soils. So these are our row totals and column totals. And what is our grand total? Our grand total is the sum of all observations, which is 76 here. Now, time to calculate the expected frequencies. So for the first cell, which is Oniscus in clay soil, so how we are going to calculate the expected frequency, 33 is the row total for this cell, and 45 is the column total for this cell. And they are multiplied, and then they are divided by 76, which is the grand total. And expected frequency is 19.5395. Then we have our next cell, which is Oniscus in chalk soil. The observed frequencies are 20, and the expected frequency is the row total, which is 43 in this case, multiplied by the column total, which is 45, and then they are divided by the grand total, which is 76. So this is the expected frequency we get for this cell. And then the next cell is the number of Armadillidium in clay soil, and the observed frequency is 8. What is the row total here? The row total here is 33, and what is the column total? It is 31. So 33 into 31, and then it is divided by 76. So the expected frequency here is 13.4605. And then we have the last cell, which is Armadillidium in chalk soil. The observed frequency is 23. And how we calculate the expected frequency? 43 into 31. So 43 is the row total here, and 31 is the column total here. So these are multiplied, and then their answer is divided by 76, and the expected frequency is 17.5395. So this is how we calculate our expected frequencies in case of a contingency table when we have to apply a chi-square test of independence. Now the calculation for the chi-square value. So we have calculated our expected frequencies, and we can see that the sum of our observed frequencies and the expected frequencies is same. Now what is the next step? We have to take the difference between the observed and expected frequency for each of these observations. So first observation, which is 25, which is Oniscus in clay soil. So 25 minus its expected frequency, 19.5395, and the answer is 5.4605. Then 20 minus 25.4605, 20 is the observed frequency for Oniscus chalk, and the expected frequency is 25.4605, and the answer is minus 5.4605. And then the next cell, which is Armadillidium in clay soil, the observed frequency is 8, and the expected frequency is 13.4605, and their difference is minus 5.4605. And the last cell, which is Armadillidium in chalk, the observed frequency is 23, and the expected frequency is 17.5395, and the difference is 5.4605. In the next step, we are going to calculate the square of the difference between the observed and expected frequencies. So the square of the difference between observed and expected frequencies of Oniscus clay is 29.8171. And then for the next cell, which is Oniscus chalk, again the square of the difference between the observed and expected frequencies is 29.8171. And similarly, we calculate the square of difference between observed and expected frequencies of our next two cells. Then in the last column, we are going to calculate our chi-square value through this method that we are going to divide the square of the difference between observed and expected frequencies by the expected frequency of the same cell.
So we are going to take the square of the difference between the observed and expected frequency of viscous clay, which is 29.8171, and then we divide it by the expected frequency of viscous clay, which is 19.5395, and our answer is 1.526. Then in the next cell, the square of the difference between observed and expected frequency of viscous chalk, which is 29.8171. It is divided by the expected frequency of the same observation, and the answer is 1.1711. Then in the next cell, 29.8171, which is the square of difference between the observed and expected frequency of armadillidium in clay soil, is divided by the expected frequency of the same observation, and the answer is 2.2152. And then the next column, we have the square of the difference between the observed and expected frequencies of armadillidium chalk, and it is divided by the expected frequency of armadillidium in chalk soil, and the answer is 1.7. Now, as a final step, we are going to take the sum of these values. So we are going to take the sum of 1.526 plus 1.1711 plus 2.2152 plus 1.7. And our answer is our chi-square value, which is 6.612. So this is how we calculate the chi-square. And then what is the next step? The next step is to calculate the degree of freedom. And degree of freedom for the chi-square test of independence is calculated by taking the product of r minus 1 into c minus 1. So r is the number of rows and c is the number of columns. So how many rows do we have in this example? We have 2 rows. And how many columns do we have? We have 2 columns. So 2 minus 1 is equal to 1, and 2 minus 1 for columns is also equal to 1, and then they're multiplied and their answer is also 1. So our degree of freedom in this case is 1. So what is our next step? So our next step is to consult the chi-square distribution table for the degree of freedom 1. So what is the first probability level that we are going to check? Obviously it is 0.05, which is the first level of critical probability, and our table value is 3.841. So what was our calculated value of chi-square? This was 6.612. So which one is greater? So obviously our calculated value is greater than the table value. So what we are going to do with the null hypothesis, are we going to accept it or reject it? So we are going to accept our null hypothesis. We are going to reject our null hypothesis in favor of the alternate hypothesis, because our calculated value is greater than the table value, which means that the probability of our null hypothesis to be true is less than 0.05. And the probability for our null hypothesis to be false is greater than 0.95. Therefore, we are going to reject the null hypothesis and we accept the alternate hypothesis. Now, what is the next step? We want to check that whether our result is significant at the next level of critical probability or no. So what is our next level of critical probability, or what is our next level of significance? The next level of significance is 99%, or the critical probability of 0.01. And what is the value here? It is 6.635. So this value is pretty close to our calculated value. So which one is greater? Our calculated value or the table value? So in this case, our table value is greater than our calculated value. Although they are close, but still our table value is greater than our calculated value. So this also emphasizes again that why we need to take as maximum number of digits possible after decimal, because we want to have an accurate result. So this is how we get our results. So what we are going to say, are we going to say that our results are highly significant or no? No, our results are not highly significant, because our probability at this level is not less than 0.01. So our probability is less than 0.05, but it is not less than 0.01. So our results are not highly significant. So once we have non-significance at the critical probability level of 0.01, then there is no need to consult the next level of critical probability, which is 0.01, because our value is always going to be less than that. So our calculated value, as you can see, is less than the table value at 0.01. So once we don't get significance at 99% level, there is no need to go for the next level of significance, because it's always going to be this. So our results are significant at 95% level alone. So we reject the null hypothesis and accept the null hypothesis, the alternate hypothesis. Now it is time to state our results, and the result is there is significant association between soil type and wood lice species. The chi-square value is 6.612 and the probability is less than 0.05. And we are stating that our results are just significant. We are not saying that our results are highly significant or they are very highly significant, because they are not significant at those levels. So our results are just significant. A probability of our null hypothesis to be true is less than 0.05, but it is not less than 0.01 or 0.001. But still, we are going to reject it because it is less than 0.05, which is the first level of our critical probability. So our result is there is significant association between soil type and wood lice species, which was our alternate hypothesis.
Now let's take another example for the chi-square test of independence calculation, and this example is about diet and health status of individuals. So information about the diet and health status of individuals was recorded, and these are the observations. And as you can remember, we had previously discussed these observations in the illustration of contingency table. So again, I'm repeating the same information. So what are the two rows about? The two rows are about one variable, which is the type of diet. And there are two types of the diets: the American Heart Association recommended diet and the Mediterranean diet. So the variable which is presented in rows is the type of diet. And the variable which is presented in columns is the health status of individuals. And there are four categories in this variable: cancer, non-fatal heart disease, fatal heart disease, and healthy individuals. So these are the observations that we have. Now the question is there any association between diet and health status of individuals? Or put it another way, is the health status of individuals independent of their diet? So this is the question that we have. So what is our next step? We have to state the null hypothesis and the alternate hypothesis. And these hypotheses are: the null hypothesis is there is no association between diet and health status. And the alternate hypothesis is there is an association between diet and health status. So these are our hypotheses. So what is our next step? The next step is to calculate expected frequencies. So expected frequency of a cell is row total multiplied by column total divided by grand total. So here we are going to calculate the expected frequencies of these cells. So these are the observed frequencies, and these are the row totals 303 and 302. And what are the column totals? The column totals are 22, 38, 33, and 512. So expected frequency for the first cell, which represents cancer cases on AHA diet. So the row total for this cell is 303 and the column total for this cell is 22. And they are multiplied and then they are divided by the grand total, which is 605. The expected frequency is 11.0182. Now the observed frequency for the cancer cases on Mediterranean diet is 7. But this observed frequency right now has nothing to do directly with the calculation of the expected frequency. So what do we need to get the expected frequency? We need to get the row total and the column total. And the row total here is 302 and the column total here is 22. So we have 302 multiplied by 22, and then their answer is divided by the grand total, which is 605. The expected frequency is 10.9818. Then the next cell, we have the non-fatal heart disease cases on AHA diet. The expected frequencies are row total 303 multiplied by the column total 38, and then they are divided by the grand total, which is 605. The expected frequency is 19.0314. And then we have the non-fatal heart disease cases on Mediterranean diet. So the row total is 302 and the column total is 38. They're multiplied and then their product is divided by the grand total, which is 605. So we have the expected frequency 18.9686 here. And then we have the next cell, which is the cases of fatal heart disease on AHA diet. The row total in this case is 303 and the column total in this case is 33. And then they are multiplied and then the product is divided by the grand total of 605. So the expected frequency is 16.5273. Then we have the next cell, which is the fatal heart disease cases on Mediterranean diet. The row total in this case is 302 and the column total here is 33. They are multiplied and the product is divided by 605. And the answer is 16.4727. Then the next cell is of healthy individuals on AHA diet. The row total is 305 and the column total is 512. They're multiplied and their product is divided by the grand total, which is 605. And the answer is 256.4231, which is the expected frequency of healthy individuals on AHA diet. Now in the last cell, we have the healthy individuals on Mediterranean diet. And the row total in this case is 302 and the column total here is 512. They are multiplied and then their product is divided by 605, which is the grand total. So we have our expected frequency of 255.5769. So this is how we calculate the expected frequencies. So here we are with the calculation of the chi-square value, again with the same table. So the observed frequencies and the expected frequencies are given in the first two columns and their sum, their total is same, which is 605 in this case. And all the categories are also given here: cancer AHA, cancer Mediterranean, and so on. So what is the next step? We have to calculate the difference between the observed and expected frequency of each cell. So the first cell is cancer AHA. The observed frequency is 15 and the expected frequency is 11.0182 and their difference is 3.9818. And the next cell is 7 minus 10.9818, which is the difference between the observed and expected frequency of cancer cases on Mediterranean diet, and the difference is minus 3.9818. And then the next cell, which is the non-fatal heart disease on AHA diet, and the difference between the observed and expected frequencies is 4.9686. And then for the next cell, this is non-fatal heart disease on Mediterranean diet. The observed frequency is 14 and the expected frequency is 18.9686, and the difference is minus 4.9686. The next class is the fatal heart disease on AHA diet. The difference between the observed and expected frequency is 8.4727, and then the difference for the next cell is minus 8.4727, and the difference in the observed and expected frequency of the last two cells of the healthy individuals, so this is 17.4231. So this is how we calculate the difference between observed and expected frequencies. Next column is about taking the square of difference between the observed and expected frequencies. We are following the same procedure. We are taking the square for each cell. 3.9818 square, which is 15.8547, and then the square of difference between the observed and expected frequency of each cell, right? So after we have taken the square of difference between the observed and expected frequency for each cell, we are going to divide that square of difference by the respective expected frequency. So 15.8547, which is the square of difference between observed and expected frequency of cancer AHA, is divided by the expected frequency of the same cell, which is cancer AHA, and the result is 1.439. Now we do the calculation for the next one. This is 15.8547, which is the square of difference between the observed and expected frequency of cancer cases on Mediterranean diet, and they're divided by the expected frequency of the same class of the same cell, and this is 1.4437. And then 24.687 divided by 19.0314, which is the expected frequency of the same cell non-fatal heart disease on AHA diet. We calculate that for the next cell as well, which is non-fatal heart disease on Mediterranean diet, and the square of the difference between observed and expected frequency is 24.687, and this is divided by the expected frequency, and the result is 1.3015. So we do the calculation for every cell. And finally, we are going to do the calculation for the chi-square, and chi-square is simply the sum of this fraction, which is the square of observed and expected frequency difference divided by the expected frequency. The sum of 1.439 plus 1.4437 plus 1.2972 plus 1.3015 plus 4.3435 plus 4.3579 plus 1.1838 plus 1.1878, and the total is 16.554. So this is the value of our chi-square. What is the next step? Calculate the degree of freedom, and the degree of freedom for the chi-square test of independence is row, number of rows minus 1, number of columns minus 1, which in this case is 2 minus 1 and 4 minus 1. So 1 multiplied by 3 is 3. So 3 is our degree of freedom in this case. Consulting the chi-square table, so 3 is our degree of freedom, and what is the level of critical probability that we look at? It is 0.05. And the table value is 7.815. So our calculated value is 16.554, which is much greater than the tabled value. So what we are going to do with the hypothesis, with the null hypothesis, are we going to accept it or are we going to reject it? So we are going to reject the null hypothesis because the probability of null hypothesis to be true is less than 0.05. Therefore reject it, and this result is significant. We accept the alternate hypothesis. Now what is the next step? Once our null hypothesis is rejected, we want to see that what is the maximum level of significance that we have for this rejection of the null hypothesis. Next level is 0.01. 11.345 is the table value. Again, we see that our result is highly significant because calculated value is greater than the table value. And then we see the next level, which is 0.001, and here we see 16.266, and this value, although it is very close to 16.554, but it is still less than 16.554. So this again emphasizes that you have to take in maximum number of digits after decimal point that you can, so that you can have an accurate result. So 16.554 is greater than 16.266, so we are going to say that our result is very highly significant. So chi-square value is 16.554, degree of freedom is 3, the table values are 7.815, at probability of 0.05, at probability of 0.01 it is 11.345, at probability of 0.001 it is 16.266, and our calculated value is greater than all of these values. So we are going to say that there is a very highly significant association between diet and health status. So chi-square is equal to 16.554 and probability is less than 0.001. That is why our result is very highly significant. So I think this is clear.